Okay. No? Okay, then the thing Dear participants, dear participants, very good afternoon to one and all. Already resource person has been joined. Kindly join all the participants. Dear participants, kindly join the session. Already resource person has been joined. Sir, thank you for joining with us, sir. Thank you, Chandrasekhar, sir.
Thank you, sir.
Sir, thank you for joining Atal-sponsored one-week faculty development program, which is organized by the Department of Computer Science and Engineering in N.B.K.R.I.S.T, sir. Thank you for accepting our request, and you are spending your valuable time, especially for this particular session, which is sponsored by the Atal agency, sir. Ma Ritika? Ma Ritika?
Yes, sir.
Yeah. Kindly, our eminent resource person, Dr. V. Chandrasekhar, sir, already joined. Kindly introduce the Chandrasekhar, sir, with all of participants.
Yes, sir. Sure, sir. Good afternoon, everyone. It's my pleasure to introduce our esteemed speaker, Dr. Chandrasekhar Varugunti, sir. Dr. Chandrasekhar, sir, is a renowned expert in deep learning and computer vision. With a PhD from IIIT Sri City and over 10 years of industry experience, including 10 years at Infosys and currently serving as lead computer vision engineer in product-based company. Sir has published over 125 research papers in top-tier conferences and journals and has conducted over 100 sessions on machine learning and deep learning at prestigious institutions like NITs and IIITs. As a senior mentor from executive programs at IIIT Hyderabad, ISB and IISc, Dr. Chandrasekhar sir has guided numerous professionals in their growth. We welcome you, sir. Welcome to our session today, sir.
Good afternoon, all. Thanks for the nice introduction. So, shall we start?
Sir, we are very much thankful for your kind participation and kind accepting our request, sir. Sir, now this session we are going to hand over you, sir, with your permission.
Sure, sir. So, let's start.
Yes, sir. Yes, sir. Yes, sir.
Okay, so let me share the screen.
Okay, sir.
Okay, so today the topic is on. Hope my voice is audible.
Yes, sir. Audible, sir. Voice is audible, sir. The screen also very good for all the participants.
Okay, so let's discuss about future of internet. So here I'm just using slides. There is no much theory. Okay, so I want to explain through the images only. Okay.
Yes, sir.
So,
Yes, sir. Please.
okay. So now what we are going to do? What is the difference? So why we need a separate internet called as quantum internet, and what are the advantages and disadvantages with quantum computing with respect to internet? Can anyone tell the participants? So why means quantum internet is required, and what are the threats? What are the damage it can do? Can anyone answer the question?
Good afternoon, sir. Maybe we are facing so many issues with the security. Our passwords are getting hacked, and it is not secure to talk. That's why we may be preferring the quantum computer.
Yes. So quantum computing is having exceptional computing advantage based upon its qubits. Okay. So we all know that the traditional computer works with bits, whereas the quantum computer works with qubits. So qubits are having the advantage of being able to exist in the multiple states together. So there are special properties like superposition, entanglement, okay, transportation. Uh, all those things makes quantum computing more powerful, especially the superposition. Okay, so if you see here, the classical computers, suppose say if I ask a question 3 into 2, okay, so what is the value? It can easily say. Or if I give the other way around, if I give 6 as an input, it can easily solve the factorization. But if I give same problem, now a bigger number, okay, so this number to split into products, okay, so it's split into products. It may take some years, a classical computer. Whereas the quantum computer can be able to split this larger number into product of two numbers, means factorization it can do. So because quantum computer brings in lot of advantages, okay, related to computation, but it is poses challenges in the area of security. It can able to breach the algorithm. So generally what happens, we are using encryption and there will be a key and the X is the data which I'm using. X is the data and I'm applying the encryption algorithm like any RSA, etc. And I have a shared key. Now this key we are using 128-bit combination, 256 combination, etc. Okay. So if I'm using the key with 128 and 256 combination, and the quantum computing is having the ability to factorize and able to work with large computations in a shorter span of time, it can able to break this algorithm and they can able to decrypt the encrypted text to get back the data. So security is what more vulnerable in quantum computing compared to the other areas. Because see, this is example. It can able to solve this problem within a minute, whereas the traditional computers may not solve at all, or they may take some years to factorize this. Okay, so see here. So RSA and all. Okay, classical computer algorithms like RSA, which are exponential time for large primes. See, but this quantum computers within a polynomial time, they can able to attack RSA or any other algorithms. And there are algorithms proposed like Grover's algorithm, etc. They can able to solve in big O of square root of n time. Okay, so why? Because can you tell me why? What is the advantage? How they're able to solve these problems in a short span of time? What is the driving force? What is the reason for this? Anyone? What is the reason? See, it is having superposition, entanglement, okay, various features, which is different compared to classical computing. Out of these, which is the factor, okay, makes quantum computing completely different compared to other classical systems? Anyone? It is superposition. So superposition is the one of the okay major okay it is one of the major technique in quantum computing which makes things possible. That means if you want to do any parallel computations, see I can suppose if my qubit is of 3 bits, then what happen in a single qubit I can able to store the information. So I can able to store all possible combinations together in a one qubit. And suppose if it is a 4 bits, then I can able to store all the 16 qubits in a single qubit. Then what happened? I can able to individually process these qubits. Now, even 10 bit, then to the power of 10 combinations, all qubits I can put into a single qubit. So the combination which I can do here, this summation of these qubits is called as superposition. And this superposition helps me to put all the possible combination, all possible qubits in a single variable. And that is what the major advantage in case of quantum computing. So rather than sending a single value, the all possible combinations which I can put into this qubit, okay, like this 0000, okay, okay, 000. Suppose if it's a 4 bit, then okay, 0001. Like this, all 16 numbers I can combine superposition and then I can put it to a single variable. So this variable I can use it to access all the elements. Okay. Now tell me, what is the advantage of having such a facility? What is the advantage of having such superposition facility? where we can put all possible combinations. Similarly, 100 also. So all 2 power 100 elements, I can put together all possible combinations in a single variable. Now, what is advantage? Can anyone tell me one practical advantage? What's the practical advantage of superposition? Anyone? Is my audio is clear?
Clear, sir. Clear, sir. Voice is clear.
Yes, sir.
Yeah, please tell me. What is advantage? Practical advantage of superposition.
Sir, maybe competitions are very faster
Very-
we can compute.
Okay. See, faster it's okay, but the advantage while computing. Tell me anyone. See, that is what you have you have to understand. If I have superposition, if I have an entanglement, okay, so how it uh, helps, how it differs when compared to quantum computing and classical techniques. And the advantage. Hmm. So having these in a single superposition variable, what is advantage? How it helps? Hmm. You might have attended the previous sessions, right? So you might have studied about this one. Okay. So how they are helpful when you do superposition? How it helps? What is the practical advantage?
Tracing is not possible, sir, between two. Like they cannot trace they move so fast that no one can trace exactly what is going in between.
Okay. Anyone? See, when you combine these two into a single superposition variable, it helps us parallelization. So parallelly, you can work with the data. Okay. So what it means is, okay. So here you have a variable, because suppose if it's a 3-bit, okay. So like this, you combined all possible combination, and that is what you are calling it as a single variable. Next, what we can do, assume that, okay, I have one slide, I'm just searching for it. Okay, then I can show you the advantages. We must know those advantages. Okay, let me check if I find I can. There is an algorithm called Grover's algorithm. So, how many of you have an idea about it? Grover's algorithm. Any idea? Let me search for this. Then I will explain what is advantage. If you have that Grover's algorithm, okay. Okay, fine. I'm unable to find it. So what happens? See here. Let's assume that there is a Oracle. Oracle means our computer. Example, our computer. So what we are doing, whenever we log in into a machine, okay, what we are doing, we will enter the password. In the backend, our computer knows the password. Okay. So let's say Sairam is a password. What the user is doing, so he can enter some password, say password 1, password 2. What it will do, it will read the password, then it will say it's not correct. It's not correct. So whenever it is correct, what it is doing, it will say yes and it will log in. This is what traditional technique. So here what is happening? Here the approach is sequential. Okay, so what you are doing, first you are trying with password 1, next you are trying with password 2, next you are trying with the last password, and that is what sequential, one by one. Whereas, suppose if you have the um, traditional this is parallel, sequential. So when you go with sequential, what will happen? One by one we have to do. So the search space or time is taken is big O of n. Now, if you go with the qubit, suppose if it's a 3-bit, what you are doing, as I said, you are combining all the possible combinations, superposition plus this. Okay, like this, you are superpositioning all these possible 8 values and you are calling it as a single qubit. This entire value, you are passing it to the algorithm, Grover's algorithm. So what the Grover's algorithm will do is, okay, so your system, see here what the system is doing. System, whenever it's a wrong password, it is giving wrong, and whether if it's a correct password, it will give you tick mark, right? This is called as a system or a oracle. Assume that you have an oracle. Oracle means some system which knows the password. So when you send this superposition value, which is equal to all possible states, then what it will do, it will, if it will reverse the sign. So in the superposition value, what it will do, suppose if 000 is not a correct password, it will reverse the sign. Okay, so sorry, if it is a correct one, okay, suppose which one is correct, others it leave as it is. So all possible combinations, okay, whichever is correct password, say suppose 111 is the correct password, then what it will do, 111, it will reverse the sign up. Okay, next, this is what the output from the oracle. Next, once we get this output from the oracle, what we can do is, so we can increase the weights. Okay, so what we will do, next step is increasing the weights. Okay, then what happens, we will take each value, okay, and because we will multiply, okay, so minus is there. So what we will do, each superposition value we will take, okay, so 100 minus, you are multiplying with, okay, some weightage, okay, some higher value you will take, and you will multiply, suppose say some higher value. Okay, this is what you are doing. Now if you see here, sorry, this side, 98 minus, okay, the superposition value, okay, so 100. Now what happens, see, 98 minus this is positive value, okay, this is the correct one. So what it will do, you are keeping some constant here, okay, some constant minus this value. Suppose this represents 0, then what happens, this will become 98. All other values, okay, because you're subtracting, but when it comes to the correct password, what happens, 98 minus this qubit value. Okay, so suppose say some 5 or 6, then what happens, it will become plus, so it will go higher value. So the weights, the coefficient, so how you are superpositioning value, alpha into 100 plus some beta into some coefficient. So whenever there's a correct one, the oracle will change the sign. So what we are doing here, there will be some constant value, say some 98, etc., anything minus of that particular each word it will write parallelly. So all are positive, only one value will be negative, which is set by oracle for the correct password, and it will get set. And then that coefficient value will increase. And that coefficient is what? Tell me. Once the coefficient increases, once the coefficient of a qubit increases, then what will happen? If the coefficient of a qubit increases, then what happens? What is the coefficient value indicates? What the coefficient of a qubit will indicate? Anyone? So these are the things you have to learn in FDP. So what is the coefficient of a qubit indicates? Anyone? So we are writing like this. So what we are writing? So we are writing like this. Okay, alpha into qubit 0 plus beta into qubit 1. Then what is the importance of alpha and beta? So this plus is called superposition, and that is what you are putting into the variable. So what is the importance of alpha and beta? Tell me. Are they just random numbers, or they convey any information? When you superposition, you are using alpha and beta. So alpha and beta are the coefficients of the qubits. That's what you are using in the superposition. What is the importance of alpha and beta? What they convey? What the information it contains? Anyone? Is my audio visible? Is it audible? Is it clear? Is my audio clear? Anyone please confirm, is my audio clear?
Yes, sir. Audible, sir. Audible, sir.
Okay, fine. Anyone? It is a simple question. So what it is? So we have superposition. We are creating a superposition, and that superposition is what the multiplication of coefficients into the qubit values. So that is how you are combining, and you are forming a superposition. What is the importance of that coefficients? Any condition is there? Anyone? Okay. So what is the importance of this alpha and beta, and what is what is the impact? See, alpha and beta are the coefficients of the qubits. What is the condition? The condition is that alpha square plus beta square equal to 1. Alpha square indicates the probability of the qubit, this one, qubit 0, and beta indicates the probability of the qubit 1. Alpha indicates the probability of the qubit 0, beta indicates the probability of the qubit 1. Why? What then? Tell me, what are these probabilities then? Now I told you, what is alpha square and beta square? Their condition must be, their squares must be equal to 1. Alpha square plus beta square must be equal to 1. Clear? They are the probabilities representing qubit 0 and qubit 1. Okay, where they're used? Anyone? Where these qubits, this probability values are used? See, any qubit, either it's a 0 or it's a 1 in the block sphere. When, see, when you flip a coin, okay, when you flip a coin, it will just flips like head, tail, etc. But when it reaches your hand, it has to turn up either head or tail. It cannot be both. But when you flip it in the air, it is containing both. So that is called superposition. Existing in more than one form is the superposition. But when you catch it, when you try to open it, it has to converge, it has to reduce into single value. Which value it will reduce? That is what alpha square and beta square represents. If alpha square is greater than beta square, majority of times that superposition value, this qubit, takes the value of, if alpha square is greater, then it takes the value of qubit 0. And if beta square is greater than alpha square, whenever you work it, when you try to open it or when you try to use it in the computation, it will converge into qubit 1. That is what alpha square and beta square indicates. So because of this superposition, if you see here, so what the oracle will do, okay, see, this is just 1 by root 8. These are the weights, these are the qubit values. Okay, so this is 1 by root 8. Can you tell me if this is say qubit 0, okay, like this, qubit 1 1 1, okay, Then what is this 1 by root 8? Can anyone tell me? What is that 1 by root 8? Why 1 by root 8? Why not any other value? Anyone? Why there 1 by root 8? Why not any other value? Anyone? So why there is a value 1 by root 8? Why not some other value? What is the reason behind it? See, as we know that every qubit value is having a coefficient. So this is qubit 0. This is qubit 1, 2, 3, 4, 5, 6, 7, 8, which is equal to 8 possible combinations. That is 2q. Next, what is this alpha 1 into qubit 0 plus alpha 2 coefficients into qubit 1. Like this, you have 8 numbers. And what is the condition? Condition is alpha 1 square plus alpha 2 square. Like this, if I add all values, then alpha 8, this 8th value coefficient whole square, it must be equal to 1. Then if you see, what is a simple one? 1 by root 8. So 1 by root 8 whole square plus 1 by root 8 whole square. If you add all 8 values, 1 by root 8 whole square, all 8 values, which is equal to 1 by 8 plus 1 by 8 plus 1 by 8, like that 8 values, which is equal to 8 by 8, which is equal to 1. The condition is satisfied. That's why it is equal to 1 by root 8. So what we are doing is, if this is the correct password, what the oracle will do is it reverses the value. See, it reverses the sign, just the sign it will reverse. This is the correct value. So what oracle will do, it reverses the sign. Then what happens? See here. If you multiply, if you want to adjust the coefficient, adjust this value in, okay. So now new weight equal to what happens? Your old weight, okay, minus your new weight. Here there is a minus. So these are all positive values. So this is a positive value. So what you are doing, you are using some weight. So it become minus. That's why 1 by root 8 is the initial weight of this qubit. Now you see, for this, it became 3/4. It got reduced. Why? Because you have chosen weight minus this positive value. This is positive weight. And now for this one, what happens? Weight equal to weight minus, as we reverse the sign, now it becomes minus 1 by root 8. Then it becomes your old weight plus new weight. When I add new weight, then what happens? The probability, it increased. And now it became 5 by 2. So 5 by 2 means 2.5. So it weight got increased by 2.5 times by 1 by root 8. And for others, it became 0.75 into 1 by root 8. So their probability got decreased. Here the probability increased too much. So as these are very less probability, okay, now what happens? The weightage, okay. So superposition equal to, which is a combination of all qubits. This qubit coefficient, which is correct one, the third one, okay. So the third one, weight will be almost 98%. So if you check, if you combine this value, compare this value, it will be 98%. Other weights will be very less percentage, 0.01 into qubit 0, qubit 1. This is qubit 3. So as this indicates the probability, whenever I use this value as my password, this will be converged to the correct password. This is the correct password. So which one is correct? For that, I am increasing the weight. For others, I am reducing the weight. And why I am able to do this? Because I have access to all the qubits. How I am access to all the qubits? Because I made them in a superposition. So that is the advantage of superposition, which makes all bits, all combination, all values available at a time to me, so that I can perform simultaneous, or I can do parallel computation. Whereas in case of the traditional techniques, I have to go one by one. So it will be sequential. It will take time. So that's what that makes the quantum computing more superior compared to the traditional. How many of you got it correct? How many of you able to understand the power of quantum computing through superposition? Anyone? Hmm. Anyone? How many of you understood? Okay, so that is what the quantum computing, which through superposition it can able to bring in all possible values together and can be represented with a single superposition value along with the coefficient and the individual qubit. I can able to access those individual qubits at a time. So based upon that, I can able to perform computations. That is the power of quantum computing. Okay. So because of its power able to perform such computations, okay, so it can able to see here. Now there is a security threat. What it is, if you see here, so what is the threat if quantum computer were developed? Sufficiently large quantum computer, if built, would be capable of undermining all widely deployed public key algorithms. Any public key algorithms, it can able to undermine. That means it can able to find out the key value. Once you get the key, you can decrypt and you can get the value. That's why, see, like this. Even though it's a very big prime number, okay, quantum computing is public key, and this is the private key developed by the RSA algorithm. They can able to quantum key can able to compute. Okay, see, such a big number. This is another big number. Two big numbers. Okay, so here what we are doing is we were able to use this qubits 0 and 1. That's why 0 and 1. So I can combine all possible to large number of even 10 to the power of 90. That means all possible states. See, 2 to the power of 10 is 1024. See, 10 to the power of 90. That means 10 90 zeros. Such a large number, which can store the information of every particle details in the entire Earth. So because quantum computing can be able to work with such data, we have just a simple 2 to the power of 128, 2 to the power of 256 keys, which a classical computing cannot break, but quantum computer can do it simply, easily. So because of quantum internet, quantum computing, there is a threat to security. And if there is a threat to security and threat to encrypted data, the main improvement we have to do in the internet. Why? Because internet is what you are using. See here, internet is what you are using to transfer your any data, social media or any data, mails, everything you are transferring through the public channel. So this is a public channel you are transmitting. This is the internet, public internet. You are transmitting the data, which is insecure. To make it secure, what we are doing, we are applying some encryption algorithms. So you are encrypting and you are sending the data, and it received by the receiver. You are performing the encryption. So you are doing the encryption. So you are taking the data, okay, and you are performing the encryption, and encryption data is going to the server. Okay, and if at all any threat, suppose if the attacker, so attacker can come in and he can hijack the data and he can see the data. He can modify, he can remove, he can take the data from the public internet, because the internet is public. No one is securing your data. You have to frame the algorithms to secure your data. So attacker can easily get the data. So then every data, all the data will be in risk. Financial data, everything. So what we are doing in case of quantum computing and quantum internet is, we all know that. So what are the driving, what are the background, on top of which concept the quantum computing is built? Can anyone answer? Which concepts it is deriving, from which subjects it is deriving the quantum computing is derived the concepts, the building blocks? Anyone tell me? What are the building blocks of quantum computing? From where it got or depended on? Quantum mechanics and quantum physics. So quantum mechanics and quantum physics, which deals with the light. Okay, that is where the quantum computing built on, based on. So now, to overcome these classical internet problems, okay, so it is working with the quantum physics and quantum mechanics, especially the light, especially the photons. So when light is transferred, light is a collection of photons. So photons are used in quantum internet to overcome these challenges getting attacked by the attackers. So what they will do? So see, this is what photon they are using, light and photons. These are light particles, photons. And these will play a major role in the quantum internet. So public key cryptography we have. So what is public key cryptography? Anyone? Any idea what is public key cryptography and how it works, or the idea behind it? Anyone? Yes, Sonika. Yes. Any doubt? Okay. So public key cryptography, we all know that there will be two keys. So one is the public key, and the second one is, first is the public key, and second one is the private key, where a public key is available to all the parties, whereas private key is available only to the communicating parties. It's private. Only the sender and receiver knows, and it is private. It is not exchanged. Whereas the public key is available and it is exchanged through internet. Whenever anything exchanged through internet it is public. We assume that everyone knows it, and by using the public key, we are encrypting the data. And that is what we are transmitting. Any financial data, medical data, okay, any secret information, financial information, or social media data, we are transmitting by using the key, and that key is transmitted over internet. So whenever anything is shared over the internet, even the public key, there are a lot of threats. Let's see here. So what is happening? Suppose Allies wants to send data to Bob. They want to exchange information. So what they will do? They will perform some public key cryptography, RSA algorithm, ECC, etc. So they will collect some prime numbers, some mathematics. Based upon the prime numbers, okay, they will compute the key based upon some prime numbers, and this key is called as a public key. Similarly, they will compute another key called as private key. So private key is not shared, whereas public key is shared. When public key is shared, okay, based upon the mathematical properties of elliptic key cryptography, the recipient can able to get the private key, but because he must have some pre-exchanged information. Based upon pre-exchanged information, the public key is from public key they can get the private key, but we assume that only these parties have the private information, but public key is available to everyone. So once the public key is available, the allies will send, see here, this is public key, this is private. Private is private or secret, whereas this public key is transmitted over the internet. So this is the internet, public internet, anyone can see the data, and this private key is changed, is sent to the from allies, okay, so from Bob to allies. So they shared the public key. Once the key is received, what allies will do? Okay, so she will prepare the data and she will perform the cryptography by using the key. And once the data is ready, okay, so what they will do, they will exchange the data through the public. So why this is public internet? Anyone can see the data, and this is encrypted. And once it receives the Bob, once the data is received, which is encrypted data with the public key, so Bob can able to decrypt the key, and he will get the message. Fine. Now what happens? Because it's a public channel, the attacker, the malicious attacker, can able to get the key. He can get the key, the public key, because it is public and anyone can access. And if he get access to any of the data, encrypted data, so any encrypted data plus the public key, they can come up with the private key. So they can perform the computations. They are expert in mathematics. By using huge computation resources, they can find out the private key. If we assume that private key is fixed and it is available to only Alice and Bob, but in the internet, as we already shared the public key, and if the encrypted data is available, both if it is available to the attacker, malicious attacker, they can able to get the private key. They can compute. And once they compute, once they compute the key and whatever information you are sending, they can able to decrypt the data. So they computed, and whatever information you are passing, so they can able to extract the data. So they will apply the key and they will get access to the information. So this is what happening in case of public key cryptography and the classical internet. And the starting point of this is prime numbers. And some mathematics, we are applying elliptic key, cryptography, etc. By using these cryptography techniques, we are coming up with the key. So that is what the problem. So here it is mathematics based, the current traditional internet and security. Whereas when in the quantum computing, we are using quantum physics and we are working with the atoms. So by understanding the atoms, further if you go inside photons, so we are depending on the quantum mechanics and quantum physics, we'll work with photons. So here what happens, in traditional, as I said, we have some public key and we have some private key, and these two keys are different. That's why we are calling it as an asymmetric key. Whereas in case of quantum computing, there will be only one key, and that's what we are calling it as a symmetric key. So in quantum computing, it's a single key, same key is shared between two users. And in classical computing, public key cryptography, there will be two keys, different keys. And this is based upon mathematics, prime numbers, etc. And here it depends upon the photons. So photons are used. Light particles are used to transfer the data and to compute the key. So these are the qubits, light particles. So qubit, various value, various position, maybe qubit 0, superposition. If this is a block sphere, so various combination, this is qubit 0, qubit 1, various superposition values are there. So each value represents one, each qubit represents a value based upon this one. So now what we will do, each light particle, this is what each light particle I am using, and this is what I am giving as a input to a polarization device. So my light particles goes through the polarization device, and what we are doing is, see here, I am ionizing. So the device, what it will do, it will polarize the light particles, and and it will map, this is the input, and for this is corresponding output. For this input, this is the corresponding output. So it will map it will convert. So each value, this is the input value, maybe 0, maybe 1, some value. We don't know what this value is, because see, this goes inside and this is the outside, and we don't know what value. Suppose if it is 0, maybe one time it may be 0, but suppose if this 0 comes out, then it may map it to 1. So we don't know. So what it will do, it will take input values and it will give the ionized values, polarized values. and like this it will compute the key. Okay, and what happens? See, these numbers is truly random. So this is 0. First it goes inside, so it may give 1. Next may be 0, but for this it may be 1. Sorry, it may be 0. So random. You cannot link the input photon to the output photon, and you cannot tamper it. We'll see. Okay, so this is what the key they generated. So input, they taken some set of qubits, and by using some ionization, they are able to produce the key. And this entire thing is light. This is light, and these are all the photons. So now see what they will do. They will develop a new channel, not the public channel. They will develop a quantum channel first. So what is the drawback in the classical system? The drawback is, first time whenever we build the key, and that key is transmitted over the public internet. So here what they are doing is the quantum key which they used through lights, and that quantum information, okay, they are exchanging, see, encoded photon. These are all the encoded photons. It means they represent the data. What data? The input. So what they will do? So see here, transmitter. Okay, they will share one this lights encoded photons. They will transfer securely. They will transfer securely a different channel through the receiver. So as and when the receiver receives, they will come to know what type of information they receive. Okay, so here transmitter is sending the data, and receiver is receiving the data. And once the receiving is done, what they will do? They will cross check. They will verify few bits, like whether what I sent. See, this is public internet, and this is a private quantum channel. This is Alice, and this is Bob. Okay, so this is internet, and this is a quantum channel. This is public, this is private. So the white photons using the device converted into this one charged photons, and that is what they used to represent the key value, and they transmitted through the quantum channel to the Bob. And once the Bob receives, they will decode, and they will cross check. And once they feel verified, see, they will verify both Alice and Bob, cross check whatever I sent and whatever you receive, both match or not. Suppose if it is matches, authenticated, yes, we both cross check when we both talk together, and they will confirm, yes, it is authenticated. Means what the Alice sent and what the Bob received, if both are same, then the authenticated. They will verify and then authenticate. Then what they will do? Okay, see, authenticated means yes, green color. Okay, the key is received correctly, the quantum key. This is a private channel. And once that is done, then what they will do? They will use that key. Okay, they will use that key, quantum key, to encrypt, and that they can be transferred through the public channel, internet, because already the key has been shared through quantum link. So they are exchanging the data. So the data is getting transferred through the internet. It will be received because they already know the key 1111100. Okay, so already they shared the key. Okay, 1111100. Okay, they shared the key, and now they will use that key to decrypt the data. See, this is internet. This is quantum channel. They decrypted it. They can see the data. Now the problem. Same thing, the attacker can come and he can use its massive computing devices, and he can capture the data. So whenever he receives the data through the internet, because the key is not shared through the public internet, he cannot decrypt the data. Once if I send the key through internet, public key, then some data samples are available. Both he can use, and then he can do some trial and error, and he can compute the private key. But if I didn't send the the key through the internet, I used private quantum channel. Now I am sending only the encrypted data through which he cannot get any clue. And suppose if you want to access the quantum channel, because of the entanglement, okay, if any damage, any see, the means whatever happens to the data will be known to both. Any changes, any damage, okay, it must be informed to the parties. It will intimate. So when he tries to just look into the data, just capture the data, then what happens? That the data gets spoiled. See, now they got changed. Earlier, what is the data they are used to transfer? They used to transfer the ions, charged photons. Okay. Now, when he tries to attack the quantum channel, then what happens? Alarm will be there, okay, and the data will be lost. See here, they will break down. They will close the channel. See, the data is lost. They will corrupt. It will become corrupt. The key becomes corrupt. Okay, so they will gracefully, alert will be there, and they will gracefully close the connection. Now the key is lost. So that is what, see, by using the entanglement, where when you open or when you check with photon, same will be reflected to another photon also. So that's what entanglement. And by using entanglement property, if anything the attacker tries to attack or looks the data, automatically they will change it. It will become correct. They will close the connection. So this is how, okay, they are able to secure the data. So see, the connection is lost now. Connection is dropped. There is no connection. So whatever they encoded through the devices, they are able to got it and they exchange it the data. And if the attacker tries to attack either the quantum channel or the internet channel, okay, here he cannot. There is no clue. Here it will drop out. Gracefully, it will get down. Okay. So what the quantum computing, quantum internet provides is unconditional data security. Okay. So like this RSA and AES algorithms are there, which easily attacked by the malicious user in the classical computing. Okay, either you do RSA algorithm or AES algorithm, whatever may be the complexity of the algorithm, there is high chances that it can be attacked by the attackers. Whereas the quantum internet depending upon the charged photons. So this is a qubit, qubit value 0, Planck sphere. So because we are using the charged photons, light particles, and we are using those particles to encrypt data. Okay, and because of the private quantum channel. And second one is the, as and when if any change data is touched or data is getting modified, automatically because of the entanglement, the other party comes to know. Then they will close the connection and they will drop the key, delete the key. Okay, so a lot of things are there like quantum encryption. So how we are going to encrypt? So that's what we have seen, photons. And see here, main thing is quantum key distribution. So quantum key distribution plays a major role. And how the key is prepared? Key is prepared like just now we have seen 10110000. How it's prepared? And it is prepared and exchanged through charged photons. And that gives the unbreakable security. Any doubts? So this is still in the research state, like it is not yet to be used. Okay, people are working on it. Okay, products are building the products. Okay, so it is still in the research state. So in US, people are building the products, and they released the videos and the white papers on how the product works. Okay, so any mathematical key can be easily broken down and can be find out through trial and error by the attacker. Whereas if you build using the photons, okay, it is very tough to break. Okay, so for that, main thing is the quantum key distribution. And quantum key distribution, like various algorithms, like how we have the algorithms for normal cryptography. So we have this encryption, quantum encryption techniques. In that, quantum key distribution plays a major role. Okay, so like this, there are various algorithms, quantum key distribution. Okay, these are the various standards available. Like we have the AES algorithm, RS algorithm. So these are the various algorithms. Okay, so key distribution. These algorithms can be used to distribute the charged photons from allies to bomb, sender and receiver. Lot of limitations are there. Same quantum computing is having limitations. So what are the limitations? Can anyone tell me what are the limitations of quantum computing? What are the limitations of quantum computing? Main thing is uh, we cannot guarantee that entanglement exists for a long time. If there is a temperature increase, or if there is a temperature drop, or if there is a noise in the temperature, so any abnormal condition can break the entanglement between the communication parties. So entanglement is what the heart of quantum internet. So if anything happens to one if source, it is reflecting the destination, then they will drop in the connection. But if the entanglement fails, then it's not guaranteed. So what are the drawbacks of the quantum computing? Say they will have the impact on the quantum internet also. Cost of maintenance. Okay. So see here, it is limited by the distance, how much distance the source and destination are. But in case of classical computing, we don't have such distance. We can just exchange the key through internet. I can send the data. But because of this dependency on the temperature, etc., see, speed, compatibility, all those things plays a major role. Okay. So it helps secure communication, and we can use it for financial transactions, healthcare, and all secure data, sensitive database applications. We can use quantum cryptography, and by using quantum key distribution, and we can transfer the data over the quantum internet. Okay. So I added some theory. Okay. So if you see here with the quantum computing, with the advent of quantum computing, even because see, they are very powerful. Because of that, current encryption methods are even more at risk, because they can able to, by using the charged ions, by using classical superposition, etc., they can able to break. See, they can able to compute the keys. They can compute the keys. Attackers. Okay. So that's what the difference between the global internet and the quantum internet. Okay. So as I explained, this is based upon the voltage, etc. Here, everything, the data is what everything is through qubits, and qubits can exist in various data, means various formats, various values at a time. Okay, and entanglement plays a major role between the qubits. Okay, the entanglement plays a major role in e-transmission. Okay, so even though they are miles apart, we can link them, and any change happens, automatically it will be known to the receiver, and they can break the connection. Okay, so main thing is C, qubits is what plays a major role in the internet data transmission. So entangled qubits is what we are using to prepare the key. As we discussed, same will be exchanged to sender and receiver, and it is not public internet over a private channel. Okay, so that's what makes more secure. And not only that, you can use it. Okay, far separated areas, quantum internet, but you can use it for see, okay, complex applications, satellite images, satellite data. Okay, the quantum computers which separated millions of distance, they can able to exchange the data. Okay, that is how uh, the quantum internet can help. So if you want to develop future internet, so there should be changes in the software, and there should be changes in the hardware, and of course the community which helps to develop various standards. Okay, there should be change in the hardware, there should be change in the software. Okay, the way you write. Okay, so how you means how you can represent the data, how the data flows. Okay, that is what we need to take care, especially the quantum processor, not normal processors, the quantum processors, who can able to understand these qubits and can able to process the superposition data. So we are bringing in the quantum processors. Okay, so QTech released the white papers. There are a lot of videos which helps us to understand how they made the product. They released the product. Okay, so by using the devices helps on top of the existing devices, it will available as a plug-in devices. You can plug in into the hardware and it will add extra security to the existing systems. Okay, but in India it is yet to come. So if you want to build a quantum internet, there should be thorough changes in the software and in the hardware in the community. Okay? Community in a sense, people can interact and they can build the data. Okay, so this is what how the quantum internet works. Okay, so I prepared this. Okay, uh, some theory. Okay, so just we will see 3 to 4. See, this is what the power of superposition. So here you can combine, like see, you can combine. These are all the coefficients. Okay, so the reminders, multiple values, and when we compute it in the cryptography algorithms, those reminders can be used as a coefficients to various qubits. So parallelly, I can work on with multiple qubits. Okay, so just some theory. Quantum internet. So future of quantum internet promises to keep messages private and secure. Okay, see, and what they're operating on? They're operating on the quantum mechanics, and that is what the science of tiny particles like photon we have seen, the charged photons. And what is the major concepts? Quantum entanglement and the key distribution. So based upon that, they're able to perform the secure communication. Okay. So see here, any attempt to eavesdrop or entangled particles alerts their states. If you entangle them, automatically, if you try to modify, the opponents will come to know and they can able to drop the data. Same, quantum key distribution also uses photons to generate the keys as we have seen, and they can able to send the encrypted data. See here, if someone tries to measure or copy these keys, the quantum states are disturbed. It will modify. It will disturb. Once it disturbs, you cannot use it for a key, and the information is lost. And they will come to know that once they receive the data, they will cross-check, and they will come to know that there is a change in the value, so they can drop the process. See here, traditional machines use encryption. It is purely mass-based, whereas the quantum internet, quantum security is based on the physical laws. So you cannot break it. You cannot, because if it's a mathematics, you can do reverse mathematics. But if you develop the key based upon the light particles, so you cannot do reverse operation on those light particles. So it's not possible to create a new key. And the main thing is, see, because if they want to share the data, means far separated areas, now they are devising new device called as quantum repeaters, and satellite links they are used so that they can able to transmit the keys, exchange the keys. Okay, so those are the advantages, and yet to means like it is still in experimental process, so it takes time so that we all use to apply those concepts. Okay, so any doubts? That's all from my side. Okay, so any doubts, any questions? Anyone? Any doubts?
Dear participants, sir is awaiting for the question and answer sessions. If you are having any queries, just you can raise the queries.
Okay, so if there are no doubts, we can drop it, sir.
Sir, please, sir. If there is any queries, give me a chance for 5 minutes, sir.
Sure, no problem.
Thank you. Respected participants.
Hello.
It is the
Hello.
time for answer session. Yes, madam. Nice, madam. Deepa, madam.
Yes, sir.
Yeah,
Sir,
kindly raise your question.
quantum computer BB84 and E91 algorithms they prefer, sir. So usually they prefer E91 better than BB84. Like, what is the thing, sir? Why they use E91? Both are almost they are using the same concept only.
See, it depends upon the computation. Main thing is computation. Second one is apart from computation, the main thing is resistance to the atmospheric changes. The quantum computing is vulnerable to change in the temperatures. Okay, so when you use these algorithms, okay, so how much like how you will transfer and how you will compute. Okay, so energy consumption, all other techniques, all metrics they will compute. Based upon that, they will decide.
Yes, sir. But actually, I don't have the environment for computing on checking for that environment because we usually go for collapse. But how I can use that energy consumption or some
See,
error rate happened?
see,
How
we
can I?
cannot quantum computing. You have to work with quantum devices. Working with collab is not going to help you. We have in India, we have only 2 to 3 quantum computers. Okay, working with collab can give you some idea, but actual vulnerability, those concepts you cannot learn when you are working with collab. It will help you to understand the things, but if you want to go dig deeper, okay, you have to work with real-time systems or IBM, Skykit, etc.
Okay, okay, sir. Okay, sir. Okay, means conceptually I can understand by collab using
As
that.
of now, we can understand conceptually, but real-time working, it will take under 5 to 6 years, where everyone can get an access to quantum computer.
Okay, thank you so much.
It will take time.
Respected participants, sir is awaiting for your queries. Sir is ready to answer. If you are having any queries on this particular session, kindly raise your queries.
Okay, if there are no doubts, yeah, we can drop off.
Yes, sir. Yes, sir. Yes, sir. Sir, thank you for spending your valuable time and accepting our request for participating the session in our Atal-sponsored one-week faculty development program on quantum cryptography enabled autonomous underwater vehicles. On behalf of the Department of Computer Science and Engineering from N.B.K.R.I.S.T, we are highly thankful to you, sir,
Thank you,
for
sir. Thanks for inviting.
spending your valuable time, sir. Ma Ritika.
Thank you, sir.
Yes,
Ma,
Thank you so much.
sir.
yeah. Ma, kindly conclude the session, Ritika. Ritika, Ritika, Ma Ritika, Ma Ritika.
Yes, sir.
Yeah. Kindly conclude the session.
Yes, sir. Yes, sir. I would like to extend my heartfelt gratitude to Dr. Chandrasekhar, sir, for his invaluable insights and expertise with us today. Your session was truly enlightening, sir. Thank you so much for your presence and valuable knowledge that you shared with us today, sir. We look forward to more such interactions in the future too, sir. Thank you once again, sir.
Sir, thank you, sir, Chandrasekhar, sir, for spending your valuable deliverables on our respected Atal sponsored faculty development program. Thank you, sir. Thank you once again, sir. Respected participants, we have a break up to 3:30. Exactly 3:30, Dr. R. Prasanna Kumar, sir, who is working as an associate professor in the School of Computing in Amrita Vishwa Vidyapeetham, Amrita University, Chennai. Sharply 3:30, session 12 is going to be start. Take a break for 10 minutes and again we will join by 3:30. Respected participants, kindly join the session. Already eminent resource person, those who is working as a senior associate professor in the Amrita School of Computing, Dr. R. Prasanna Kumar sir already joined. We are requesting you, all the participants, kindly join the session. Sir, very good evening, sir. And hearty welcome to our respected faculty development program. Yes, sir. Sir, we are very much grateful to you, sir. Again, you are accepting our request, and at first session regarding yours, we are receiving very good feedback, sir. Same way.
Thank you so much, sir. It was my pleasure actually to be part of this meeting. It was really nice.
Yes, sir. Yes, sir. Sir, we are very much thankful, sir, on behalf of the Department of Computer Science and Engineering from N.B.K.R.I.S.T for accepting your request as a sincere manner. Thank you, sir.
Thank you, sir. Thank you, sir. Sir, I'll share the screen now. Just 1 minute, sir.
Yeah, sir. Sir, 1 minute, sir.
Sir?
Sir, 1 minute, sir. 1 minute, sir.
Yeah, okay.
Sir, our Ritika is awaiting for your introduction, sir. With your permission, we are going to give us introduction, sir. Ma Ritika, kindly introduce the Dr. R. Prasanna Kumar, sir.
Yes, sir. So good evening, everyone. It gives me an immense pleasure to introduce our esteemed resource person for today's session, Dr. R. Prasanna Kumar, sir. Dr. Prasanna Kumar, sir, is an experienced academician with extensive contributions in computer science, focusing on artificial intelligence and quantum machine learning. With 25 years of experience in computer science and engineering, Dr. Kumar, sir, is currently serving as an associate professor and head of student welfare at Amrita Vishwa Vidyapeetham, Chennai. Dr. Kumar, sir, has successfully guided a PhD scholar and is currently guiding 10 scholars as well. Sir holds patents for 3 innovations related to damage assessment in thrust bearings, battery management systems for electric vehicles, and AI communication protocols. Dr. Kumar, sir, has authored multiple resource papers in reputable journals, focusing on topics like data mining, natural language processing, generative AI, and quantum computing. Sir has published in top-tier Cuban journals and has 130 papers to his credit indexed in Scopus with an H index of 13. We are truly honored to have such a distinguished and dedicated academician with us today, sir. Thank you so much for joining our session today, sir. We eagerly look forward to an insightful and enriching session ahead. We welcome you once again, sir.
Thank you, Ritika. Sir, with your permission, we are going to hand it over the session, sir. Prasanna Kumar, yes, sir, kindly accept our request, sir.
Yes, sir. Thank you so much. And sir, I hope my audio is clear, right?
Yes, sir. It is audible, sir. Your audio is audible, sir.
Okay. I'll share my screen.
Madam, kindly stop your video, madam.
Yes, sir. I think you can see my screen, right, sir? Sir, can you see my screen?
Sir, your presentation also more visible to us, sir.
Okay, thank you. So I'll just go for the presentation mode. Okay, good afternoon, one and all. So I have to thank the management of N.B.K.R.I.S.T College who has given this opportunity to me to be part of this wonderful event. I think it's the last day.
Madam, kindly unmute your video, madam. Kindly stop your video, respected video.
Yeah, fine. So thank you, sir. Thank you, Chandrasekhar sir, for this wonderful opportunity. So today's topic is really a wonderful one, right? Since I'm extensively working in quantum machine learning, particularly with relevant to bioinformatics, I think this topic is of great interest to me. So it's my pleasure to be part of this topic, like quantum machine learning. Uh, so uh, sorry. Yeah. So leverages quantum principles. So in the last class, I think when I was part of this session, I handled about the quantum hardware, right? So how the hardware actually is designed for quantum computing. So it's a, I told you, like, it's a kind of what is it? Computer organization and architecture class, and we had a wonderful time at that. So now the agenda is like there are 5 key points that you can take away from this class today. One will be like what is this quantum and what is machine learning, particularly with respect to AI, and what is the fusion between these two. Okay, how these two technologies actually converge into each other, and how these two technologies will be helpful in bringing out wonders in technology. So this is the first introduction part. Followed by that, we'll have some foundational concepts. I know that we are having very less time, but anyway, as far as possible, I'll just try to give you more insights about the foundational concepts of quantum ML or QML. And then we'll discuss about few algorithms and approaches. And of course, any of my presentations, what I do is I take care that what is the impact that is creating in the society, particularly like real world impact on using any particular technology. So we'll have some applications and use cases related to quantum machine learning. And of course, what is in store for researchers in the future if one wants to take research in quantum machine learning. So where and what type of advantages and what type of the scope it has got. So these are the 5 takeaway points that we'll be discussing in today's class. So first, starting with my presentation, the first one is about the emergence of quantum machine learning. So actually, it's a wonderful concept. 2 fields, 2 revolutionary fields we are discussing today. One is quantum computing, and another one, of course, is artificial intelligence. Since then, when we started using ChatGPT, right, all are talking about AI now. Wherever you go, people talk about artificial intelligence. You go for a political meeting, people talk about AI. You go for a medicine conference, medical related conference, people talk about AI. You go for some business people, talk with a business person, they talk about AI. So quantum and AI, actually, they are revolutionizing the technological aspects. So here, there's one statistics that I have included from Precedence Research. You can see, right? So it says that the global quantum ML, quantum AI market, okay, is approximately, it will grow to something like $351 million US in 2024. Okay, so and it will not stop here. They are saying that it will grow something like around 6.96 billion US by 2034. 2034 is like another 10 years from here. So it is like approximately a growth of 34.8%, nearly 35. You know, such growth is phenomenal. The Indian economy grows something around 6 to 7%, and that itself we are seeing wonderful results. So just think about 35% growth in a particular technology, right? So it is a very much promising field any researcher can rely upon. Okay, wonderful research problem statements are available in this particular domain. So, to make you all understand about what is this machine learning, what is quantum computing, and you are saying that it will converge or there is some common thing between these two. So I just wanted to show you like how actually this particular fusion or convolution is happening. Okay, so you can see this Venn diagram. I think all are very familiar with Venn diagrams, right? So we have this one circle towards your left and one on your right. So the one that's on your left talks about artificial intelligence. Like you can see that the topic I have given. So one talks about artificial intelligence, and on your right we have another thing which talks about quantum technologies. Okay, now coming into this artificial intelligence domain, so there's some subset which we call it as machine learning. You can see that it's a subset. We have this machine learning, and of course, like we have another subset deep learning, and we have another subset large language models. We all know that large language models is creating a lot of buzz among the technology community. You all know why, right? So can you answer me why large language models are creating disruption in the technology arena now? Can you just share it in the chat? Someone? Okay, can someone post it in the chat, like why all are talking about large language models? Okay, see, I think all are using chat GPT, am I right? How many of you here is not using chat GPT? Please answer. You post it in the chat window. You say that, so till now I have not even used a single prompt in chat GPT. Anyone? Okay, so I think last class was very much interactive, and I'm not finding any answers today. What happened? So is it due to the last day syndrome? Okay, no problem. I'll proceed. So large language models like ChatGPT and all, people are using it extensively, right? So that's why large language models, it's a fusion of machine learning and deep learning. So nowadays, multimodal large language models are emerging where you can get information like or content generated in text, in video, as well as images. Am I right? Audio also. Of course, it generates music also, right? Okay. So now talking about the other side, quantum computing. So quantum computing has like quantum communication. I think we discussed about how communication happens between the qubits and all. So quantum communication is one part, and it of course uses n number of sensors to gather data and to process that data. So here you can see in the middle, like there's an interaction that happens between these two disruptive technologies like AI and quantum technologies. Now, coming to this AI, you can see that it has got machine learning, deep learning, large language models, etc. On the right hand side, you have the quantum communication. So it includes, actually, that's very important. This quantum communication also includes like, sorry. So it includes the relevant cryptography theme of this particular conference, right? So underwater communication. And then, of course, like the shaded area, which you can see, this is the crucial interaction or the converging area between these two technologies. So what will happen is that this will aid in a number of areas, like it will help in drug discovery, it will help in cryptography, it will help in drone technology, So it has got abundant applications, and a number of people will be very much interested in using this convergent technology, quantum ML. Okay, so it is like, I can say three important points. Maybe if you want, you can take it down. One is it will help in accelerated growth. So the second one is it will help in disruptive innovation. And of course, like the third one is the drastic technological changes. So these are the impact that this particular convergence will help. Okay. And then here is a comparative study, like between the classic machine learning algorithms. I think most of you might have studied or might have been worked in this one machine learning, right? The classical machine learning algorithms, like classification algorithms, clustering algorithms, etc., etc. And now coming to this other part now, what is this quantum machine learning? And this is a comparative table, right? First of all, let me tell, like with respect to their processing capability. Okay, so the classic machine learning, the main problem is that it actually is limited to the Moore's law, right? So Moore's law, I think you know that. Can someone tell me what is Moore's law and how it constrains the hardware growth? Anyone? Okay, no problem. Actually, what Moore has said that is in an integrated circuit like IC, the number of transistors while integrating will be doubling approximately every 2 years. Okay, this was the one he said in something around 1960s. Okay, between 1960 and 1970. So this was his original law. Okay. Exactly to quote that law, it states that the number of transistors on a microchip doubles in every 2 years. Okay, so this is what he said, which means that there is a huge limitation on this classical machine learning hardware. Whereas coming to this quantum machine learning, the processing capability is phenomenal, in the sense it has got huge processing capability with exponential processing power. We all know that it has got that third degree, right? Like in qubit and all, we have discussed about it. To a third state is there, right? Okay. And then coming to the data handling capability, you all know that everyone today generates huge volume of data. Am I right? Like we generate data by taking photographs. We even now we are generating data by this online session. So a video is being generated, audio data is generated. So if you use Google Maps, data is generated. Huge volume of data is being generated by each and every individual. It's not that only scientists generate data, only doctors generated data. That was once. Nowadays, even like for example, if you take at the transport department, every person who is driving an auto, they generate data using Google Maps, right? So data is generated by everyone. This is one example. So handling such data and the large scale of data is really a challenge in the basic classical machine learning, whereas quantum machine learning has the capability to efficiently process large scale, very complex data. So this is the second difference I just wanted to quote here. The third one is the efficiency of the algorithms. Okay, so if you just consider the classical machine learning algorithms, they are like polynomial or the time complexity. You all know that two important factors we studied. One is time complexity, another one is space complexity. Coming to the algorithm efficiency of classical machine learning, they are either polynomial or sometimes exponential, right? Whereas coming to the quantum machine learning, it has huge potential for polynomial time solutions, which means that the time required to solve very much complex problem will be very less. So the algorithm efficiency is greatly improved in this quantum machine learning. Coming to the accuracy also, it's not only efficient, but also it's very much accurate. So due to limited computational feasibility, the accuracy is not that much great in our classical machine learning algorithms, whereas in quantum machine learning, the accuracy is far better for data pre-processing, data processing, as well as the algorithmic design. Okay, the final advantage of quantum machine learning over classical machine learning is about the scalability. So what is scalability? For example, if a system can handle 100% per second, if 1,000% per comes into that and asks the system to handle those persons, it may not be doing it efficiently. So scalability is a problem. And particularly in classic machine learning, due to the limited availability hardware and the processing capabilities, it really impacts the scalability. Whereas quantum computing promises greater scalability, and due to the hardware advancements, we all know that each and every company like Google, IBM, Intel, they have their own hardware for quantum, right? So with the advancements in this quantum hardware, scalability of complex algorithms will be very much easier. So any point, like, I can strongly vouch that quantum machine learning is much more advantageous when compared with a classic machine learning algorithms. So now you can see a nice diagram over here, and but this diagram actually talks about the basic differences. So can someone tell what is there on the top? It talks about okay. So maybe here it talks about the classical data zeros and ones, and here it talks about the quantum data, the qubit, which has got like superposition of states between zeros and ones. Coming to the time, you can see that the time taken by the classical machine learning is huge. You can see that here. Whereas here you can see that quantum machine learning processes the algorithms in very less time. You can consider that the shaded portion is the time taken. Okay, so here you can see that more space is shaded, whereas here it is very less. Now coming to the diagram which is on the bottom, you can see like how this quantum machine learning actually processes information. So we have this classical machine learning algorithms here, and then the quantum machine learning algorithms over here. So what is the basic difference? See, coming to this classical machine learning, CML, okay, let me call this classical machine learning or as CML. So classic data is given into that, the algorithm or the machine learning thing, it processes this data. Okay, so once it is done, like the output is given to the user, right? Whereas coming to this part, the quantum machine learning, what happens here is the same classical data, actually this classic data is to be transferred into QD, which means that the quantum data. Okay, so quantum data, in the sense, it has to be converted like qubits. You can see that here it is like if n is equal to 3, let me consider that there are 3 bits, only 3 options are available here. Whereas if n is equal to 3, then in quantum machine, it has got 2 power n, which means that it has got 8 possible states available. Okay, so this quantum data generated with this qubits is given to the quantum machine learning, which processes, and you can see this shaded portion over here. The first transformation is the classic data is transformed to quantum data, and once the quantum machine learning processes this data, again this quantum data is transformed to classical data, so that the output remains the same. Okay, so this is like the processing model of the quantum machine learning. Coming to this applications, we have like face recognition, genetics, entertainment, recommender systems, finance, and of course, like one in the self-driving automation. Actually, one of my student is working in this automation of what is it, autonomous car or autonomous driving thing. So what is the work he is doing is that in order to reduce the processing time, see, even a nanosecond delay in taking some action will be what is it, fatal in any automobile, right? So in order to reduce the delay, he is using quantum machine learning, and that work is in nascent stage. He's still working on it. Okay, so actually what I can say is, like, this particular slide says that I'm not going to replace this classical machine learning with quantum machine learning. Okay, CML is not going to get replaced by QML. Please be clear in that. So what it is going to, it's a synergy. Okay, it's not replacement, but a synergy is going to happen over here. So both these algorithms, quantum machine learning and classical machine learning, can work together, which will have very good impact. Okay, so the very high impact areas, maybe there are a number of areas I have discussed here, but the very high impact areas generally will be in genetics, genetic engineering, finance, and of course in the self-driving sector, that is autonomous driving. Okay, so this is about the synergy that is between classical machine learning and quantum machine learning. Okay, maybe I'll just stop over here. If you have some queries in the slide or till now, whatever we have discussed, you can either unmute and ask, or you can post it in the chat window. Maybe I'll give some 30 seconds time so that we can, get it clarified if you have some doubts. Okay. Fine. Then I'll just move on to the next slide. So the next slide, what we are going to discuss is about the foundations of quantum machine learning, or QML. Okay, so what we are going to discuss about here. So, like, we have already discussed certain advantages of quantum machine learning over classical machine learning, but still diving deep more into like what's happening. Okay, we should know much more about what's happening over here. So the thing is that if you have worked in machine learning, you might have heard about this term curse of dimensionality, right? So what we do is when we have a number of dimensions, we try to select only certain features and then reduce the dimensionality of the data so that processing can be made easier. Am I right? So this challenge, that is the dimensionality challenge or the high dimensionality challenge, is solved or is taken care by quantum by using this parallelism. Particularly it uses superposition. Okay, there's a concept called as superposition which helps in doing this particular thing. And then for solving complex problem, particularly like genetic engineering or certain thing related to image processing, particularly high resolution image processing and all, we need exponential resources. That is the requirement of the resources, particularly the hardware, software. It becomes huge in classical machine learning, whereas quantum, it requires only like, it's not that much high, since it has got certain hidden correlations via entanglement. And coming to this, like the NP-hard optimization is really difficult. For example, some routing problems in a network, drug discoveries, etc. Whereas here we can optimize that efficiently by the concept called as interference. So you can see the three words: superposition, entanglement, and interference, and how these three solves the problem that are arising in CML or the classic machine learning. And then we have like the energy and rising memory demands, like it requires huge memory and all. So by speeding up the pattern recognitions and certain things optimization, we can efficiently reduce such requirements in quantum machine learning. Now, it was just an introductory sessions. Now, what is quantum machine learning? What is the exact definition of quantum machine learning? You can see it over here. Like quantum machine learning is the study of how these quantum algorithms can perform or accelerate machine learning tasks. Okay, like we'll be using the principles of quantum machine learning over here, and then try to make use of this quantum principles like entanglement, superposition, etc., to improve the nature of work. Okay, and why do we say that this quantum machine learning is very unique? It extends machine learning into the quantum domain. That is the interesting part of this, right? We know what is machine learning, but this quantum machine learning actually extends the basis of machine learning by leveraging the qubit properties. That is the third state. Okay, but still, this NISQ era. You know what is NISQ? Anybody? No idea. Okay, so we call it as noisy intermediate scale quantum era. I think I told in the last class. Okay, so it's mostly like hybrid models rather than fully quantum as of now. Coming to this nature of quantum machine learning, I think it uses hybrid approaches. It's not working on its in tandem. As I told you, it's not going to replace machine learning, but it will be working along with it. There will be a synergy between these things, right? So you can see that it combines the classical computing, particularly data pre-processing and optimization, with quantum computing. Okay, it has this VQCs. I think we discussed about quantum circuits. Quantum circuits, in the sense, I just told that word, but I did not teach much about that in the previous session. But I think you might have heard this quantum circuits in some other session, right? So it works with this variational quantum circuits for the learning tasks. And it actually focuses on classification, regression, clustering, and optimization. Which one? The quantum machine learning. Now, this talks about the basic quantum principles. The first one is superposition. I think I'll just skip off this slide, since you might have studied about these things earlier also. But anyway, I'll just tell what is superposition. So here we have like the third state. We have 0, 1 represented within these brackets, or both simultaneously. That is what we call it as superposition. It enables parallel representation, which is highly impossible in the traditional system. Okay, so this superposition is the foundation of quantum parallelization. The next one is entanglement. So here is a nice example of how this entanglement actually works. Okay, so what is this entanglement and how it actually works? You can see this coin toss analogy. Coin toss analogy was here. So here we have like two balls entangled in a box. Okay, so you can see that the two colors of the balls are either yellow or red. Okay, so they are in a position of superposition. That is like they are both yellow and red at the same time. Okay, but when you observe that, we can say that it is yellow. You can see that over here, these two persons, they say that mine is yellow, and another one is also accepting that is also yellow too. Similarly, here you can see that there's a second opinion. This girl says that it's red, and this guy also says that it is also red. Now, the main advantage of entanglement is that the objects, they remain connected over vast distances. Distance is immaterial over here. Okay, so here the scientists think of entangled objects as really a single object. It's not that a number of objects are over there. So now coming to the third one. Okay, if the same ball is looked at some other different angle or some other side, it may again go to the superposition state where 50% will look like yellow, another 50% of the ball will look like red, as you can see here. Okay, but if the second observer looks the ball from another side, okay, it may look like yellow. You can see here both, right? So the balls are still entangled, but the viewer, how the viewer sees that actually decides whether it is yellow or red. So this is what we call it as entanglement. Okay. Another thing is the interesting example we are going to discuss is about the quantum kernel method. So it differentiates how this classical machine learning actually differs from the quantum kernel, right? So here you can see the same 4 dimensions, like I think in graph you might have seen that x, y, minus x and minus y. So 4 dimensions, sorry. It's a graph with 2 dimensions, not 4. Okay. So there are certain data points here like A, B, C, D, E, F, G and all, they are connected with each other. Now the same thing is embedded into a quantum space. We call it as the quantum Hilbert space, or which you can see it on the right hand side. So what happens over here? Right? So we are representing the data in the classical machine learning in a 2-dimensional area, whereas you can see here this right hand side top, we are embedding that into quantum Hilbert space. Okay, so this classic data is large high dimensional quantum feature space, which this quantum feature space is called as the Hilbert space, right? So we use this quantum circuit. We will be designing a quantum circuit to map each of these data points like A, B, C, D, etc. to a complex quantum state. So you can see here one circuit for A, one for B, one for D, H, F, G. You can see some quantum circuits over here, right? So this we call it as, maybe I can call it as a richer space when compared with the normal 2-dimensionality space here. You can see here. This particular space, the data structure can be revealed. That's very interesting. Whereas here, the structure of the data will not be revealed in this classic machine learning. Okay. So, even though we see that the data points are scattered randomly here, in both the cases, it's now very clear that they have their own separable patterns, right? They have their own separable patterns, which can be like redraw the map which has been already drawn over in the previous classic machine learning. Now, what about this? Okay, what we do here? See, in this we can see the classic machine learning, the data points C, G, and E. They have certain things, right? So, what happens over here? This particular mapping, you can see even here the same mapping between G, C, and E are here, right? So the final result is nothing but the quantum computer or this quantum kernel, what it will do is it will calculate the new relationships, okay, between the data points. The new relationships may be like the distances or similarities between all the points in this high dimensional space. Okay, so what is the output? The output is nothing but this one, which we call it as the quantum kernel. Okay, so this quantum kernel is given again back to the quantum machine learning. So this particular quantum enhanced perspective about data, the classical algorithm can easily identify the patterns that exist. Okay, so here the takeaway point over from this diagram is that we have to think of the quantum computer as some special lens or a special specs or kind of stuff, where our data, when it is look like something which is inseparable, not particularly oriented, when we saw in our normal eye, whereas when we look through this quantum kernel, maybe I said that it's like a lens or a spec, something like that. When we look the same data using this quantum kernel, what it will do is whatever we felt like jumbled, inseparable and all, the hidden structures, okay, are made very clear. It is like maybe the hidden relationships are made very clear, allowing to easily solve whatever problem we want to solve. So this hybrid quantum classical approach is, as I told you, like we are not going to take away the classical approach. We are going to use a hybrid method. The hybrid quantum classical approach is a promising path which will help us to solve n number of real world problems. Okay, so if you have any doubt in this, maybe I'll just pause for some 30 seconds. You can ask.
Respected participants, sir will be assigned a respected time for 30 seconds for question and answers. Up to me. Kindly raise your queries if you are having any. Having any doubts up to now in this particular session, just raise your doubts.
Okay, now let's move on to the next slide. Okay, we are talking about QML, synergy, hybrid approach, blah, 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 right? Now, we will talk about the taxonomy of this quantum machine learning, or we can say the framework that we are going to use. So, here is a small diagram that will like help you to understand certain nuances of this framework. Okay, so we can call this maybe as a matrix, a 2x2 matrix. Am I right? So it has got some 4 values, 2x2, based on 2 things. One is the type of algorithm that we are going to use and the type of data, right? So these are the 2 things. One is like we can go for the classical data and classical machine learning algorithms. This is one approach. So we have 4 quadrants here, right? So as I told you, it's based on the data and based on the algorithm. Now, the first thing, it's nothing but you can see classical, classical, which means that it uses classical data with the classical algorithms. Okay, so this is nothing but the traditional machine learning. Maybe some neural networks running on GPUs analyzing text input or image input or audio input. Okay, so this is what we are presently doing, all of them, right? Coming to the next one, classical quantum. What is this classical quantum? So the second one, which is shaded in blue color, classical quantum, here it refers to the classical data and quantum algorithm. Okay, so this is very much promising. This is a very interesting as well as very much promising area where most people who are working in quantum ML are working on. So here we take real world data, real world normal classical data, and use a quantum computer to find the patterns. Instead of giving it to the normal hardware, we give it to the quantum hardware or the quantum computer, which takes care of the processing. So we all know that in the previous slide, I told that quantum kernel will give you a nice understanding about the hidden patterns and all. Similarly, here also, this particular quantum computer uses the quantum computer will give us a clear understanding about the hidden patterns, right? Okay, so the next one is like quantum classical. You can see here, my mouse pointer is there. What is this quantum classical? Quantum data, classical algorithm. Okay, so what is this quantum data? Classical data, we all know whatever data we are using, maybe a CSV data or image data or a video data, etc. Now, what is this quantum data? So we use a classical computer like our normal systems, whatever we have with GPUs, CPUs, etc. But we are going to analyze data that is from the quantum source. That is the important thing here. It's not like the data that is generated normally. Okay. For example, we can think of some scientists running a quantum simulation of a molecule, right? I think we all know what is a molecule, atom, etc. So the output data is quantum in nature. Quantum in the sense it will be like the three dimensions that you have, and they might use a classical neural network to analyze this quantum data. Okay, an example is like a quantum quantum data generated by analyzing certain molecules and all. Okay, so the next thing or the last part is like the quantum. What is this quantum? Can someone tell me now?
Dear participants, kindly respond.
Okay. So here we use quantum data as well as the quantum machine. Okay. So it's like a very long-term perspective, which like nearby future we may not be using that. Normally we are using this classic quantum now. Okay, maximum applications are running in this classic quantum method, where the classic data is used and quantum computers are used to solve them. Okay, but now coming to this quantum, it involves like quantum data as well as the quantum computers. The quantum computer here will learn directly from another quantum system. Okay, that is the quantum data. Perhaps to design a new quantum material or quantum algorithms, it will be used. But this is not that much still popular among the research community. Maybe soon it may come. Okay, so I think this will give you an understanding about how this QML actually works with the data and the algorithm. Any queries in this? Maybe you can post it in the chat window. I'll just answer it. Okay, fine. Let's move on to the next slide. So the next slide talks about the classical data plus classical methods. Okay, I think the examples are self-explanatory. You can easily see them. Right? It is traditional ML, example, logistic regression, neural network, decision trees, etc. So the relevance is it uses the baseline used to compare against QML performance. Like the performance of machine learning will be checked with the performance of the classical machine learning algorithms. Okay, by using this with the quantum algorithms. And the next one is like classical data and quantum models. So what we do is classical data sets are encoded into this quantum states by using this quantum kernels. I showed one diagram related to quantum kernels. No, so using those quantum kernels, they are encoded and then it is given to the system. Example algorithms are quantum SVM, QSVM, and then we have QNN, Q neural networks, and we have VQC, which means that variational quantum classifiers. So most of the algorithms today run on this method. Whoever are working in quantum computing, they work on this methods. Okay. So the next one is quantum data plus classical model. Okay. So as I told you, like the data is generated by some scientists using some molecular research and all, and this is given to a classic machine learning algorithm, and they try to solve this. Particularly, it is relevant in quantum physics, chemistry, material sciences, etc. And then, of course, as I told you, it is future oriented. It's not feasible as of now, but people may start working soon or later. So this is about the taxonomy of quantum machine learning. Now let's just see, actually the thing is, before going into this, I just wanted to make one thing clear. This session is just for some 90 minutes, and I just wanted to give you a bird's eye view of the concepts in QML. So I'm not taking any specific algorithm and then explain this, since it may take a lot of time to deep dive into any particular specific application, specific algorithm, and also generally I'm saying all those things. Now coming to this part, we are going to discuss about the core quantum machine learning algorithms and the frameworks that exist. So first application or the first algorithm is related to predictive analytics. So you can see some nice diagram over here. which talks about 5 algorithms. One is the quantum support vector machine, or in short, we can call QSVM. Okay. And then next to that, like we have this QPCA, that is, we know what is PCA, right? Principal component analysis. Here we have this QPCA, which means quantum principal component analysis. And then we have here at the bottom quantum neural networks, so which talks about the basics of neural networks. And then we have this Hasidim-Lloyd algorithm. So this HHL, it's a circuit diagram. I'll just explain that with the circuit diagram later. And then we have this approximate optimization algorithm, that is QAOA, quantum approximate optimization algorithm. We will be discussing about this one by one. Okay. So first one is like how to solve some linear algebraic problems. Okay. So for solving some linear algebraic problems, what we do is, let's take, for example, we can begin with the key application area. So many of the most important machine learning algorithms or the tasks is like a recommendation engine or some data analysis using PCA. So they are basically linear algebra problems, this PCA and all, right? Okay. So what they do is they manipulate large matrices by multiplying them or doing some linear algebra problems. Okay. So it actually becomes a natural fit for the quantum computing. Okay. So the quantum computers are actually built for this particular applications like PCA. So here what happens is that an n qubit quantum state is a vector, right? You know what is vector data, right? So you can see here this high dimensional vector spaces are created over here in this quantum. So the quantum gates, I think you might have heard about quantum gates, right, in the previous section. So the quantum gates are actually the matrix transformations. You know what is matrix, what are the transformations in matrix, etc. So you can see that the quantum circuits actually perform this matrix transformations, and it can solve like Fourier transformations, the eigenvalues, linear equations, etc. So an example is that HHL, right? So this HHL algorithm is a very famous one over here. It's named after 3 persons. So one is Harrow, Lloyd, and Hasidim. Okay, HHL, Harrow, Hasidim, and Lloyd. So it's named after these 3 people. So it is designed to solve systems for the linear algebraic problems or linear equations. Okay. So when it is used properly, it actually provides an exponential speed up over any classical algorithm. Okay, so it is proven that QML, particularly for linear algebraic problems, is doing wonders. You can see at the last, HHL algorithm gives exponential speed up. You all know that exponential speed up is a great achievement, right? So it is really, really of great use. And then the next one is showing the circuit diagram of this HHL. Okay, maybe I'll just explain a bit, not take much time over here, but here what happens, okay, you can see like the qubits are represented on the left hand side. Okay, this is just a high level overview. I'm not going to have this in-depth thing. So the circuit diagram looks maybe like a complex one, but let's analyze this gate. I think everything is a gate over here, and how this actually works. So we can say that it has got 3 main stages. Okay, I can split this entire diagram into 3 main stages over here. The stage 1 is nothing but the quantum phase estimation. On the left hand side, you can see over here, phase estimation, right? So this is the first stage. So it is actually, maybe I can call this as a subroutine or some functions like what we use in the classical algorithms. So this is a very famous quantum subroutine. It is used for finding the eigenvalues of the matrix. Okay, I repeat again. This particular what is it? Stage of this HLL algorithm is used to find the eigenvectors of the matrix, and once it's done, it encodes them into the middle register. You can see some registers over here, and it is encoded over here. Okay, this is the first stage. Next one, you can see that is the C rotation. So the C rotation is also called as controlled rotation. Okay, it's in the middle. You can see here the C rotation. It's also called as controlled rotation. So what happens here is it performs the rotation. Okay, on top of the ancilla qubit, you can see there's ancilla qubit is given over here. It performs the rotation over here critically. Okay, so the angle of rotation depends upon the inverse of the eigenvalues. Okay, so we have just found the eigenvalues over here in the phase estimation. So based on this eigenvalues, the rotation, the controlled rotation actually happens. So this is the first step where computation actually happens, C rotation. Okay, and then the last part you can see is nothing but the inverse phase estimation. Okay, this is the final stage. It reverses the first step to uncompute the intermediate information. It cleans all the registers, whatever is used, and then what will happen here is that the result of this will be you can see here the input register is here at the bottom. Okay, so the input is over given to this phase estimation. From this phase estimation, after certain things, it goes to the C rotation, and then the inverse phase estimation happens over here. And the final output you can see here emerging out of this HLL algorithm. So it is a foundational example of how the quantum principles can be orchestrated to solve classic hard problems and make them commercially viable to solve. Okay, I'm not going in depth as I told you due to lack of time. And then the next one is like PCA, quantum principal component analysis. So the previous HHL was about eigenvectors and how it actually deals with this eigenvalues. Now coming to this QPCA, it is one among the most famous algorithms on date. What it does is like, you know what is PCA, right? What is the use of PCA? I think I mentioned in the slide also. Can someone read that and just type in the chat window? It is it is used for? Okay. It is used for dimensionality reduction. You can see over here, I just mentioned this in the presentation itself. So it is used for dimensionality reduction, and it can handle only smaller data sets. It cannot be in a position to handle bigger data sets, and it is easier. It's a very easy machine learning algorithm. Okay, when the number of features increases, when the dimension increases, this PCA will not be in a position to work, particularly if it reaches some millions of attributes. So what we do here is like we have this classical bottleneck. So the bottleneck is that the scalability. So it requires calculating the eigenvectors and eigenvalues of the data's covariance matrix. You all know that how this PCA works, right? So for a data set, for example, with millions of features, this matrix becomes impossibly large, right? We cannot do the calculations, and also the calculation becomes intraceable. We cannot trace whatever is happening over here. This is a classic, the bottleneck that occurs in this classical principal component analysis, or we can say that PCA. Now, what is this quantum approach? Or we say that it's a quantum PCA. So it is used to solve this main problem, dimensionality curse, right? So how it actually works. It uses a combination of certain advanced techniques like QRAM. So what is this QRAM? QRAM stands for quantum RAM. You all know what is RAM, right? RAM stands for random access memory. So this QRAM actually, what we'll do is we start loading the data into this QRAM basically, okay, into the quantum runs. So then what we do is there's a process which we call it as density matrix exponentiation. You can see over here. First, the data is loaded into this QRAM, and then we perform an action which we call it as density matrix exponentiation. So what it will do is it will efficiently prepare a quantum state to represent a covariance matrix. You all know that PCA works based on matrix, certain things and all, right? So it all works on this. Okay. So next what will happen? We go for the third part, which we call it as the quantum phase estimation. You can see that the data is loaded, and then we go for the density matrix exponentiation. So this is actually what happens is that efficiently it prepares a quantum state, okay, and that represents a covariance matrix. So once this is done, the last stage is nothing but the phase estimation. So what happens in this phase estimation is the same thing that happened in the previous slide. I think the previous slide talks about HHL, right? So here it is very similar to this HHL algorithm where that rotation and all happens, and then we find the inverse of these eigenvalues, right? Okay. So it rapidly finds the eigenvalues of the state, and it does the work. The main advantage of this quantum principal component analysis is that it achieves the exponential speed up. As I told you, like exponential speed up is really wonderful for what is it? Solving n number of complex problems, as I told earlier, like the genetic engineering problems, etc. Now, this is a quantum circuit, and how it is used to prepare this quantum principal component analysis. Okay, so here this is just a conceptual view, nothing much we are going to discuss over here. It's an overview only. It also is like quite complex for a fresher, like the one who is going to start about quantum techniques. But anyway, I'll just explain it as simple as possible. Okay. So what is the aim of this particular circuit? So it is used to take a quantum state, okay, representing this high dimensionality. We all know that we discussed that high dimensionality is a problem. What is it? Particularly in PCA, am I right? So in order to solve that, this particular QPCA will be helpful to us. So what actually is present here? So here we have like a sophisticated eigenvalue finding routine. So again, a subroutine is present here, which is used to find the eigenvalue. It is like the other machine learning algorithms, normal machine learning algorithms. Okay, so we have also an eigenvalue estimator here, which is also called as the quantum phase estimation. Okay, so you can see here PE, which means that the quantum phase estimation is done over here. It actually effectively calculates the eigenvalues of our data's quantum state and encodes this information into a set of ancillary qubits. So these qubits will be used for further thing. And then we have like another part, quantum extraction. So what it will do is this quantum extraction in this particular thing, you can see here 2 and 3, right? So the block 3, I can call this as the third block. So this third block So this is the second block. The second block, what it does is it does this agent value estimation. And coming to this third block over here, this third block is used for component extraction. So it is like a filter. It uses some gate. You can see here swap gate. Can anyone tell me what is a swap gate? Okay, actually, maybe a swap gate is nothing but fundamental 2-qubit operations can be done over in this. It is used to exchange the states of 2 qubits, right? We can exchange the states over using the swap. The normal swap operation takes place over here. Fine. So it uses a swap gate. It is used to compare the quantum states and allow to project out the measure uh, for a particular principal component. Okay. So here it explains about the circuit. This is a design circuit for QPCA. And the next algorithm is like quantum support vector machines. So as I told in the previous thing for PCA, we'll just discuss about what are the disadvantages of a classical SVM over here, and then we'll just check how quantum SVM will be helping us to solve the problem faced by a normal SVM. Okay, so we all know that SVM stands for support vector machines. So generally it is used for classification and regression. I think we are all very familiar with that. So how does it work? Can someone put that? So it will find the best possible boundary. Am I right?
Yes, sir. Yes, sir.
Yeah, it'll find the best possible boundary to separate the data points into different categories. So we can classify based on that. Okay. So for complex data, basically what a classical SVM does is like um, it uses that boundary and separates. But there's a problem when it, again, this high dimensional data, when it comes, basically there will be the curse of dimensionality picture coming in, and the algorithm will be struggling to work. So now the two concepts of quantum thing, one is superposition and entanglement, actually leverages this SVM. That is particularly if you go for quantum SVM. So again, the same like PCA, this quantum SVM also provides exponential speed up for classical tasks. Okay. Now this is a quantum circuit. Don't worry if you're not understanding about the circuits and all. This is just for your, as I told you, it's a bird's eye view. I'm not going in depth. Okay, since my intention is to tell what are the algorithms present and to give you a basic structure about how it will look. Okay, so don't feel bad that you are not able to understand everything now. You just know this, and maybe when time permits, you can go, drill deep down into the concepts, and then you can work using this tools like Qiskit and all. Okay, fine. So coming to this quantum circuit for this SVM. Okay, so the main aim is to create a circuit that can perform the kernel method. I think we discussed about quantum kernel a bit earlier, right? So here we use feature maps. Okay, so it is the most important component of this gates. The feature maps are used over here, and these feature maps job is to take a classical data point and encode that as a complex high dimensionality quantum state. I think we saw that in the previous diagram, right? So, and we have the inference structures over here in this. The inference structure, which uses the Hadamard gate, you can see that H here, the Hadamard gate at the beginning and the end, you can see here. right? At the beginning and the end sandwiches the feature maps between, creates the phenomena we call it as the quantum interference. So this creates the quantum interference over here. So this is a circuit that we can use it for quantum SVM. Now, the next topic or the quite interesting thing is, okay, PCA, SVM and all, they work with numeric data, right? What about other type of data, whether quantum computers will be in a position to work on those other type of data? Means the answer is like, we have deep Q learning, or we can call it as DQL. So what is this deep Q learning about and how it actually works? So it is nothing but, till now we are talking about machine learning, am I right? Classical machine learning, or in short we call it as CML. Now we are going to do like another thing with respect to deep learning. Can someone tell what is the use of deep learning? Okay. So generally deep learning uses what? Neural networks, and basically they are designed to handle what type of data? Image type of
Image
data.
data. Image data.
Yeah, that's good. Fine. At least I can hear some voice now. It's really good. Fine. So this deep quantum learning actually combines, as I told you, deep learning with quantum computing. Okay. So it is used for training the system in a faster manner. So it handles multi-layer perceptron with reduced complexity. We all know that deep learning is like the what is it? Circuit is really complex, but whereas here the quantum circuit makes them simpler. Okay. And research have proven that this deep quantum learning outperforms GPU clusters in scaling large models, particularly with huge data. So this qubits acts as neurons. Okay, here this is the transformation phase. The qubits access neurons mimicking the neural network in the hardware. It enables like deep learning beyond the classical limit. We all know that classical system still has a number of problems. Okay. So now the next slide shows the deep quantum learning what is it, structure. So you can see that this is basically a hybrid structure. It's a hybrid approach. Okay. So this particular diagram like shows the training of quantum neural network, and you can see like we have a quantum data set over here, a quantum model over here, and then at the end you can see evaluate the classical model, right? So that's why I told that it's a quantum approach. So there are like 3 steps over here. What is the first step? The first step is the quantum part. Okay, you can see here the quantum part. In the quantum part, we begin by preparing our data. You can see that data is prepared over here. Then once the data is set, you are prepared, you all know that it has to be given to a quantum circuit. A parameterized quantum circuit is built over here. You can see that, right? So this parameterized quantum circuit will process whatever data is given into it. So this is what we call it as a quantum model. Now the next stage, or maybe the second step, I can call it as the classical model over here. So what we do is we get output from this quantum model, and then we get output from this classical model. So the classical data is fed into this classical computer to evaluate the cost function. We all know that cost function and how it is used in evaluation. So we evaluate a cost function which will tell us how well our model is performing. Am I right? So next, the last one is the feedback loop. You can see here. So we actually evaluate the gradients and upgrade the parameters over here. Okay, so our loop is here. This is the most critical step since based on whatever the cost, the classical optimizer will evaluate how to update the parameters and in the quantum circuit and to improve the results. Okay, So what I can say from this particular slide, maybe the takeaway point is that this is a very powerful collaborative process that happens between quantum computing and classical deep learning model. Okay. So the quantum computer does the heavy lifting of the processing. That is, all the high dimensionality data is taken care by the quantum machine over here, while the classical computer, what it will done is run the optimization loop. You can see over here, right? So this hybrid model, many people are working. If you're really interested in doing some deep learning work, maybe you can try to incorporate that. So the next slide we'll have like an comparison chart kind of stuff, like which will tell about the quantum optimization and quantum machine learning. Okay. So what is this quantum optimization? There are certain takeaway points over there. One is discrete optimization. Another one is continuous optimization. And then we have the mixed integer programming, and then multi-objective optimization. Okay, so here the goal of this is to find the best possible solution from among a vast number of options we have. Okay, so the two prominent among those are listed over here. One is the VQE. I think it is mentioned over here, the variational quantum agent solver. And then the next one is like QAOA, which means that quantum approximate optimization algorithm. So this VQE, variational quantum agent solver, is a hybrid algorithm. Okay, generally they started it for chemistry, for the chemistry department. It is used to find the lowest energy configuration of a system. Okay, that is how this actually came into picture. The next one, QAOA, which is also called as quantum approximate optimization algorithm. It's again a hybrid algorithm designed to find high dimensional approximate solutions to complex combinatorial problems. It's really interesting. And then we have like SDP, which is nothing but semi-definite programming. We have Hamiltonian descent, and we have central path methods. Coming to the next one, the quantum machine learning, you can see like the classic methods are supervised, unsupervised, and reinforced, whereas here you can see like quantum neural networks, quantum kernel methods, quantum SVM, and of course for GAN also we have quantum GAN, and of course we have for topological data analysis QTDA. Okay, so maybe I can say that out of this particular slide, we can maybe conclude that QML is a rich and a diverse field. Okay, it's not like what we think. It's the powerful optimization, quantum optimization techniques like VQE, QAOA. They are very commonly used to train the models in quantum machine learning. Okay, so this is just giving a broader algorithmic landscape that we can use in quantum optimization and quantum machine learning. Okay, any questions here? Okay, so to conclude with, okay, anyway, we have other discussions. As of now, we have given, or I have given some overview about certain quantum algorithms like quantum SVM, quantum PCA, etc. And then we compared with the merits of quantum computing when compared with the classical computing. Also, a few hybrid approaches were discussed over here, which makes the system more efficient also. Okay, so next we'll move on to the applications of this quantum machine learning. I think I have given some intro about the applications, but anyway, we'll be discussing much about the research perspectives of quantum machine learning. So you can see like on the top, quantum simulation is there. What it will do is it is used in applications like drug design and material design. You all know that materials is playing a key role now. Everyone talks about materials, right? So if I take the traditional drug discovery process and all, they are very slow and it will take more time and all, whereas quantum simulations are very much helpful. Maybe I can tell one example where when people were affected with COVID, the vaccination was discovered within months. But whereas when people were similar pandemic has occurred in the human history earlier also. It's not that COVID is the only pandemic. Maybe we know about COVID, but before that also, like plague and all, people got affected. It took years for them to design drugs. Okay, but just think about a situation where COVID is in place and the scientists are taking some years to find the drug. Almost the entire human fraternity might have been vanished, right? So classical algorithms, classical machine learning algorithms and deep learning algorithms, to some extent, they are helpful, but this quantum simulations actually will speed up such simulations and results will be obtained much faster. And we have here like the enhanced quantum computing. Normally, it is used for designing computer codes, compile the quantum circuits, etc. And this QML also which has another perspective which we call it as the machine perception. So it is used for sensing like quantum system dynamics, physics, etc. And then of course we have the classical data analysis. It speeds up the optimization, supervised and unsupervised machine learning tasks. What will be the future of this? That's very interesting. So quantum computing, particularly in data analytics, since most of the research that happens in the academic community, particularly in India, countries like India, is revolving around this data analytics. So what is in store? Okay, so what is it? It is overcoming the quantum barrier in quantum analytics now, and it has enhanced computational capabilities. It is revolutionizing machine learning and AI. It has a great impact on big data. I think we all know what is big data, the V's of big data, etc. So it is impacting a lot on big data and also security. I think a number of sessions were there on security. So it also helps very much in data security. Okay, so this will be the future. And I have just listed some use cases for quantum computing, particularly in banking and financial services. So you can see like it is used for portfolio analysis, fraud detection, like credit card frauds, etc., optimization, and then cyber security, and then high frequency trading, asset valuation, grouping, clustering. So these are a few applications that is use cases of quantum computing, particularly in finance and banking. And then this is another example for quantum drug discovery where I'm not going to explain this in detail, but I can say that how drug discovery will be aided by using this quantum computing power. Okay, so the next one is like, what are the key takeaway points from quantum AI for the problems that the current AI actually is facing? So you can see that the present AI, it requires high resources, optimization. We have a number of bottlenecks and we lack interpretability and there are computational limits. So you can see here, like we can efficiently use the resources, we can enhance optimization using quantum. There is an improved transparency from the lack of interpretability, and then we can overcome this computational limits. So with this, we'll move on to the next section. The next section talks about the challenges. See, I say that it is resource efficient, optimization can be enhanced, improves transparency, blah, blah, blah. But what are the challenges, right? So still the challenge lies in the hardware, the basic hardware. Like you can see, the error correction is a challenge. The stability of the qubits is a challenge. Scaling of quantum systems is a challenge. Quantum algorithms and software development, it is in nascent stage. Only few people are working in this. So still a lot of work is to be done. And of course, the hardware cost is too huge for any normal person to handle. And then, of course, quantum supremacy and verification is to be done. So these are few challenges. With this, we'll move on to the next slide, like what will be the future, right? Then the future is about improved accuracy, training the system quickly, and we have to apply it in other fields. We are using only in materials and drug discovery now. We have to use it in other fields also, and we have to go for new algorithms specific to quantum computing instead of just going for the hybrid models alone. So with this, I'm concluding today's session, since I like generally conclude before 5 minutes, and I give 5 minutes time for the audience to ask some questions if they have any. So you can find my details over here. I think I have shared the last class presentation. So maybe I'll just share this presentation also in the PDF format. Since this doesn't have any video and all, I'll just share the PDF alone, so you can have a look at it. And if anyone is really interested in doing some cutting edge research, particularly in quantum machine learning, you can contact me either phone or in LinkedIn, or you can mail me. So I think two of my students are working in quantum machine learning. One application is for drug delivery. It's not drug discovery, but drug delivery, particularly for cardiovascular diseases. We call it a CVD, cardiovascular diseases drug delivery. One of my research scholars, I think she's going to submit the thesis maybe by in another 1 or 2 months. And another one scholar, as I told you, he's in Germany. He's working in an autonomous car manufacturing plant in Germany. He is working in quantum machine learning to improve the decision making process, like how effectively and how fast decision making can be done, particularly while the system or the autonomous vehicle is moving. So that's all for this session from my end. If you have any questions, maybe you can ask. Meanwhile, I'll just share the presentation with your coordinator, Chandrasekhar sir.
Sir,
Yeah.
sir, yes, sir. Yes, sir. Yes, sir.
Yeah, you can share it with other people, sir.
Yes, sir. Sir, you can forget one more your scholar. He is more humble and most respected person, sir. Your scholar, Dr. B.S. Shauri Rai, sir. He is
he is about. I think he has submitted his synopsis.
Yes, sir. Yes, sir. Yes, sir.
Actually, he is working in blockchain technologies. Yeah.
Yes, sir. Yes, sir. Yes, sir. He is very good for everyone in our department, sir. He's having very good insight.
Yes, sir. Even whenever he comes and meets me, he's really, really humble.
Yeah. Yes, sir. Yes, sir. Yes, sir. Yes. Sir, thank you, sir. Thank you for spending your valuable time and valuable deliverables and accepting our request as a sincere manner.
Thank you, sir. Thank you so much. It's my pleasure, actually.
Atal-sponsored one-week faculty development program on quantum cryptography enabled autonomous underwater vehicles, sir. Without any violations, without any interruptions, you only the person you are accepting our request, and you are delivered a wonderful deliverable, sir. We are receiving very good feedback from our previous session also, sir. Now itself also we are receiving very good feedback, sir. Dear participants.
Thank you so much, sir. Thank you.
Sir, thank you, sir. Dear participants, sir is awaiting for your question and answer session. If you are having any queries regarding this particular session, just raise your queries on the chat box.
Okay, Deepa ma'am has asked to share the number. Ma'am, maybe I'll just text it here also for your convenience.
Yes, sir.
But anyway, it is there at the end of my presentation also. Yes. This is my
last slide, your communication details.
Yeah.
The contact details will be there, sir.
So, and my mail ID also I have shared, so you can use my mail ID, and maybe you can WhatsApp and you can ask some questions. And okay, another one, I think few technical queries are there. I'll just take it up one by one. So what is the first one? Like how to develop quantum lock scheme with the phase kickbacks to target multi-qubit registers. Okay, Srikanth sir has asked one question. So basically, like the purpose of what is this lock schemes is to what is it? one minute. I'll just read the question back again. Now, how to develop quantum lock scheme with phase kickback to target multi-qubit registers. Okay. Yeah. So basically, this phase kickbacks uses entanglement properties. So using that, we can transfer, what is it? We can allow for the transfer of phase information from a target register to a control qubit. Am I right? I think you understood what is target register control qubit, since your question is something related to that. I assume that you know all those things. So actually, this kickback circuit and maybe an ancilla qubit, it is prepared in a superposition state, and we use an Hadamard gate for it. This gate will act as the control qubit. Okay, so which is for a control unitary gate, okay, which will be applied to the target register. So when the target register, which is an agent state of the unitary gate, what will happen here is the agent values phase is kicked back to the control qubit. Okay, so maybe like you can think of what is it? Two Hadamard gates, and we have like the input given, and the kickback is done by using this ancilla qubit. Okay. Okay, and then is it difficult to implement on real hardware when phase kickback is present? Yeah, it's still a challenge and people are working on it. Yes. Sashikant Panta. Yes, sir. Okay, I think I got very good feedback from your organizers. But anyway, even you can post your feedback. I think they'll have a feedback form, I think, right? Okay.
No, sir. No, sir. We received very good feedback, sir. Really, we are telling.
Okay, thank you, sir.
Really, we received very good feedback from our organizers. Sir, from the Department of CSE, N.B.K.R.I.S.T, once again, thank you for accepting our request, and you are participating more than one session in our adult-sponsored one-week faculty development program, sir. Thanking you for your valuable time and valuable deliverables. And we are receiving feedback from your presentation and from your material, sir, what you can share in our adult-sponsored group, sir. Thank you, sir. Thank you, Prasanna, sir. Thank you.
Thank you so much, sir. Thank you.
Thank you, sir. Thank you, sir.
Yeah, thank you, Shauri, sir. Nice to see you.
Sir, thank you, sir. Thank you very much, sir.
Nice.
Sir, good evening, sir. Sir, please share the second session feedback link.
Already shared, sir. Already shared. Once again, as per your request, we are going to share it again, sir.
Thank you, sir.
Yeah, thank you, sir. Dear participants, the next session, the eminent resource person, Dr. Koduru Harikrishna, sir, is already joined the session. You can take a break for 5 minutes and you can join the session. Dear participants, kindly take a break for 3 minutes. And the eminent resource person from the Department of Physics, having the abroad exposure, Dr. Kodur Harikrishna sir, has been already joined. Respected participants, very good evening to one and all. Now we are in the session 13 on our Atal sponsored faculty development program on quantum cryptography enabled autonomous underwater vehicles. Now in this session is going to be handled Dr. Koduru Harikrishna sir, who is having the international exposure and did a work in quantum physics in abroad. Currently, he is working as a associate professor, Department of Physics in N.B.K.R.I.S.T. Now, we are very much thankful for accepting our request and participating and delivering the valuable deliverables. Thank you, sir. Thank you, Harikrishna, sir. Ma Ritika, kindly introduce the Dr. Koduru Harikrishna, sir. Ritika. Respected participants, kindly join the session. Ma Ritika, kindly introduce our respected resource person for today's session 13, Dr. K. Harikrishna Sarma.
Yes, sir, sure, sir. So, good evening once again to one and all present here. Today's resource person is Dr. Harikrishna Koduru, sir. Sir is selected as the Bulgarian National Speaker Belong in NIE Fellowship in the year 2019, and sir has joined as an experienced researcher in Georgi Magico Institute of Solid State Physics. Sir's current research work aims to fabricate and characterize the multi-layer structure polymer nanocomposites for energy conversion and storage applications.